At Krasnoyarsk-26, a sprawling nuclear production complex in Siberia, routine liquid waste operations functioned exactly as designed throughout 1967. Monitoring systems recorded normal radioactivity levels in designated discharge channels. Safety protocols governing effluent release operated within established parameters. Environmental assessments confirmed that the facility's impact remained within projected boundaries. Engineers trusted decades of validated calculations that modeled radioactive dispersion through controlled pathways into the Yenisei River system. Yet by autumn, contamination had spread through river networks in patterns that contradicted every prediction. Not through equipment malfunction or procedural violation, but through hydrological processes that the facility's environmental models had never incorporated. The safety calculations that governed daily operations assumed static water flow, predictable seasonal variation, and contaminant behavior that followed laboratory-derived dispersion coefficients. When spring snowmelt and unusual precipitation altered river dynamics, radioactive material moved through sediment transport, groundwater infiltration, and floodplain interaction mechanisms that existed outside the analytical framework used to justify the facility's discharge practices. The contamination at Krasnoyarsk-26 represents a failure of environmental modeling, rather than operational control. The facility operated within its design parameters while spreading contamination through pathways that its safety assessments had systematically excluded from consideration. Every procedure was followed. Every calculation was correct according to its assumptions, and yet those assumptions rendered the facility's environmental impact fundamentally unknowable. The Krasnoyarsk Mining and Chemical Combine, designated as Krasnoyarsk-26 in Soviet nomenclature, represented the culmination of nuclear engineering confidence in environmental management during the late 1960s. Located in the remote Siberian taiga approximately 50 kilometers northeast of Krasnoyarsk City, the facility housed 3 plutonium production reactors designed according to principles that had governed Soviet nuclear operations since the establishment of the first production reactor at Mayak in 1948. The reactors designated AD-1 and AD-2 operated within a technological framework that treated environmental discharge as a controlled, predictable process governed by well-understood physical laws. The facility's environmental safety philosophy rested on mathematical foundations that had been developed during the Soviet Union's rapid nuclear expansion of the 1950s and early 1960s. These foundations embodied 3 core assumptions that would prove catastrophically inadequate when tested against the complex environmental realities of the Siberian watershed. First, that radioactive materials released into water systems would behave according to laboratory-derived dispersion models that assumed uniform flow conditions and predictable dilution rates. Second, that the Yenisei River system represented a stable hydrological environment where seasonal variations remained within calculable parameters derived from historical flow data. Third, that monitoring systems positioned at designated discharge points could provide comprehensive surveillance of the facility's environmental impact through measurement of key radiological parameters at strategic locations. These assumptions reflected the state of environmental modeling in the 1960s, when computational limitations forced engineers to rely on simplified mathematical representations of complex natural systems. The theoretical framework that guided environmental protection at nuclear facilities had been developed primarily through laboratory studies and small-scale field experiments that could be conducted under controlled conditions. These studies provided reliable data for predicting contaminant behavior in simplified systems, but they bore little resemblance to the dynamic variable conditions present in large-scale river systems with complex geological and hydrological characteristics. The reactor cooling systems at Krasnoyarsk-26 operated according to engineering logic that viewed the Yenisei River as an essentially unlimited heat sink with predictable thermal and radiological absorption capacity. The AD reactor, commissioned in 1958, operated on a once-through cooling system that drew water directly from the river, circulated it through the reactor core to remove fission heat, and discharged the heated, slightly contaminated water back into the river through a carefully designed outfall structure located approximately 2 kilometers downstream from the intake point. The design calculations that justified this approach assumed that the massive flow volume of the Yenisei averaging over 600 cubic meters per second, even during low-flow periods, would ensure rapid dilution of radioactive materials to levels well below established safety thresholds. The AD-1 and AD-2 reactors, commissioned in 1961 and 1964 respectively, featured closed-loop cooling systems with heat exchangers designed to minimize direct contamination of cooling water while still utilizing the river for ultimate heat removal. These systems represented an evolution in reactor design that reflected growing awareness of environmental protection requirements, but they operated according to the same fundamental assumptions about river behavior that governed the earlier once-through design. The heat exchangers isolated the primary cooling circuits from direct contact with river water, but they still relied on massive volumes of river water for cooling the secondary circuits that removed waste heat from the reactors. The environmental dispersion models that justified these discharge practices had been developed using computational methods available in the early 1960s, when electronic computers remained primitive by later standards and mathematical modeling required significant simplification of complex physical processes. The Soviet nuclear establishment had adopted dispersion equations that treated river flow as a one-dimensional transport problem with uniform velocity profiles and predictable mixing characteristics. These equations assumed that radioactive materials discharged into the river would follow surface water flow patterns and would be diluted according to simple mathematical relationships that related contaminant concentration to distance downstream from the discharge point. The regulatory framework that governed environmental protection at Soviet nuclear facilities embodied confidence in mathematical modeling that reflected broader technological optimism characteristic of the nuclear age. The State Committee for Nuclear Safety had established radiological discharge limits based on calculations that assumed worst-case meteorological conditions and conservative estimates of public exposure pathways. But these calculations relied on the same simplified environmental models that guided facility design. The regulatory approach treated environmental protection as an engineering problem that could be solved through adequate mathematical analysis and proper implementation of calculated safety margins. The facility's environmental monitoring program reflected these modeling assumptions through systematic measurement of radiological parameters at locations and frequencies determined by theoretical predictions of contamination transport. Monitoring stations positioned along the Yenisei River downstream from the discharge outfalls measured water column radioactivity, using detection equipment calibrated to identify the specific isotopes and activity levels that the dispersion models predicted would result from routine reactor operations. Additional monitoring stations measured airborne radioactivity and surface contamination in areas surrounding the facility according to patterns predicted by atmospheric dispersion models that had been validated through meteorological studies conducted during the facility's initial licensing process. The instrumentation used for environmental monitoring represented the state of radiation detection technology available in the 1960s, when electronic systems remained relatively primitive and required careful calibration and maintenance to provide reliable measurements. The monitoring equipment installed at Krasnoyarsk-26 could detect gamma radiation and beta particle emissions at sensitivity levels adequate for identifying contamination above regulatory limits, but the instruments provided limited capability for distinguishing between different radiological sources or for detecting contamination that might accumulate through environmental processes not considered in the original safety calculations. The operational procedures that governed routine discharge operations embodied the assumption that environmental impact could be controlled through careful adherence to calculated release limits and systematic monitoring of predicted exposure pathways. Plant operators received training that emphasized the importance of maintaining discharge rates within established limits and promptly reporting any monitoring results that exceeded predetermined action levels. The procedures assumed that operators could maintain effective control over environmental impact by following discharge protocols that had been derived from mathematical models and validated through regulatory analysis. The reactor designs themselves embodied assumptions about the relationship between nuclear technology and natural systems that reflected the engineering confidence characteristic of the nuclear age. Each reactor operated at design powers exceeding 1,400 megawatts thermal, generating enormous quantities of waste heat that required continuous cooling water circulation. The design calculations that determined cooling water requirements assumed that the Yenisei River possessed essentially unlimited thermal capacity and that heated water discharged into the river would be rapidly mixed and cooled through natural processes that could be predicted using standard heat transfer equations. The waste management systems associated with reactor operations reflected similar assumptions about the predictability of environmental processes. Liquid wastes generated through reactor operations were processed through treatment systems designed to remove radioactive materials to levels that would ensure compliance with discharge limits when diluted in the river system. The treatment systems operated according to removal efficiencies that had been determined through laboratory studies and small-scale testing, but they had never been validated under the complex environmental conditions present at the actual discharge location. The facility's safety culture embodied confidence in mathematical analysis that reflected broader Soviet technological achievements in nuclear reactor design and space exploration. Engineers trusted their calculations because those calculations had proven reliable for nuclear reactor design and operation, where controlled conditions allowed mathematical models to accurately predict system behavior. They assumed that the same analytical approaches would provide equally reliable predictions for environmental systems, failing to recognize that natural systems operated according to processes that were fundamentally more complex and less predictable than engineered nuclear systems. The environmental characteristics of the Krasnoyarsk-26 site had been assessed through geological and hydrological studies that provided data on soil composition, groundwater flow patterns, and seasonal variations in river flow. But these studies had been conducted using survey methods that could not fully characterize the complex environmental processes that would govern long-term contaminant transport. The site selection process had identified the location as suitable for nuclear operations based on criteria that emphasized remoteness from populated areas and adequate water supply for reactor cooling, but environmental protection considerations remained secondary to operational requirements in the decision-making process. The hydrological models used to predict contaminant dispersion in the Yenisei River system had been developed using flow data collected over limited time periods that did not fully capture the range of seasonal and climatic variations that could affect river behavior. These models assumed that future flow patterns would remain within the range of historical observations, and that unusual hydrological events would not significantly alter the basic assumptions underlying environmental safety calculations. The models treated the river as a relatively simple transport system with predictable mixing characteristics, failing to account for complex interactions between surface water flow, sediment transport, and groundwater infiltration that would ultimately determine the actual environmental fate of discharged radioactive materials. The contamination pathways that would eventually create the environmental disaster at Krasnoyarsk-26 were already present in 1967, embedded in the hydrological and geological characteristics of the site that the facility's environmental assessments had inadequately characterized. Seasonal patterns of precipitation and snowmelt created temporary flow conditions that violated the steady state assumptions built into the facility's dispersion models. Sediment deposits in the river bottom and floodplain areas provided mechanisms for radioactive material accumulation that existed outside the analytical framework used to justify discharge operations. Groundwater infiltration patterns created subsurface contamination pathways that could transport radioactive materials beyond the reach of surface water monitoring systems. The stage was set for an environmental disaster that would unfold exactly as the system had been designed to operate, creating contamination through processes that remained invisible to the monitoring and control systems that were supposed to prevent such releases. The mathematical models that justified routine operations would prove adequate for predicting system behavior under the simplified conditions for which they had been developed, but they would fail catastrophically when tested against the complex environmental realities of large-scale nuclear operations in a dynamic natural system. The environmental contamination at Krasnoyarsk-26 emerged from latent modeling deficiencies that had been embedded in the facility's design from its inception. These deficiencies did not represent oversight or negligence, but rather reflected the systematic limitations of environmental science and computational modeling capabilities available in the 1960s. The facility operated exactly as intended while creating pathways for contamination that its safety assessments had never considered. The most critical modeling gap concerned the hydrological behavior of the Yenisei River system during periods of unusual precipitation and snowmelt. The environmental assessments that justified the facility's discharge practices assumed that river flow would remain within historical parameters that could be characterized through statistical analysis of existing data collected over approximately 15 years of systematic measurements. These assessments failed to account for the complex interactions between seasonal flooding, sediment transport, and groundwater infiltration that would govern the actual movement of radioactive materials through the watershed during extreme hydrological events. Soviet nuclear facilities operated according to discharge protocols that had been developed through laboratory studies and small-scale field tests conducted at research installations, where controlled conditions allowed precise measurement of contaminant behavior under simplified environmental scenarios. The mathematical models used to predict contamination dispersion assumed uniform mixing, steady-state flow conditions, and simple dilution processes that would minimize radioactive concentrations through massive water volumes characteristic of major river systems. These models worked perfectly for the controlled conditions under which they had been validated, but they bore little resemblance to the dynamic, variable conditions present in real river systems with complex seasonal flow patterns and geological characteristics. The facility's environmental monitoring program reflected these same modeling limitations through systematic placement of detection equipment at locations determined by theoretical predictions rather than comprehensive environmental assessment. Monitoring stations were positioned to detect contamination along pathways that the dispersion models predicted would carry the highest concentrations of radioactive materials downstream from the discharge outfalls. This monitoring strategy created systematic blind spots for contamination that moved through mechanisms the models had not considered, particularly contamination that might accumulate in sediment deposits, infiltrate groundwater systems, or concentrate in floodplain areas during high water periods. The monitoring equipment itself was calibrated according to contamination levels and isotope compositions that reflected theoretical predictions rather than the complex mixtures that would result from real-world environmental processes. The radiation detection instruments installed at environmental monitoring stations had been designed to measure gamma radiation and beta particle emissions from specific isotopes that reactor operations would discharge in known quantities and ratios. The instruments provided reliable measurements for the radiological signatures that safety calculations predicted, but they possessed limited capability for detecting contamination that might be chemically or physically altered through environmental processes that changed isotope ratios or created unexpected radiological signatures. Organizational factors within the Soviet nuclear establishment reinforced these technical limitations by creating institutional pressure to minimize environmental concerns that might interfere with production objectives that remained paramount during the height of nuclear weapons development in the 1960s. The facility operated under directives that prioritized plutonium production schedules over environmental protection measures, creating operational practices that systematically pushed discharge levels to the maximum limits allowed by existing safety calculations. These practices remained technically compliant with established safety protocols while exploiting the gaps in environmental understanding that made those protocols inadequate for protecting against contamination through unpredicted pathways. The training and expertise available to facility operators reflected the state of environmental science in the 1960s, when radioecology remained a nascent field with limited understanding of complex environmental processes that governed long-term contaminant transport and accumulation. Operators possessed detailed knowledge of reactor systems, radiation protection procedures, and nuclear safety protocols, but they lacked the environmental science background necessary to recognize that their discharge practices might create contamination through pathways that their monitoring systems could not detect. The training programs that prepared operators for nuclear facility work emphasized reactor physics, mechanical systems, and radiation safety, but they provided minimal instruction in environmental science, hydrology, or ecosystem dynamics. The facility's safety culture embodied confidence in mathematical modeling that reflected broader technological optimism characteristic of the Soviet nuclear program during its period of rapid expansion and international competition. Engineers trusted their calculations because those calculations had proven reliable for nuclear reactor design and operation, where controlled conditions and well-understood physical processes allowed mathematical models to accurately predict system behavior within acceptable uncertainty ranges. They assumed that the same analytical approaches would provide equally reliable predictions for environmental systems, failing to recognize that natural systems operated according to processes that were fundamentally more complex, less predictable, and more variable than engineered nuclear systems operating under controlled conditions. The environmental monitoring data collection procedures reflected modeling assumptions about which parameters would provide meaningful indicators of environmental impact. Monitoring protocols emphasized measurement of water column radioactivity at specific downstream locations, atmospheric radioactivity near the facility boundary, and surface contamination in areas where the dispersion models predicted that airborne releases might deposit radioactive materials. These protocols provided comprehensive surveillance for environmental impact that followed the pathways that mathematical models predicted, but they remained systematically blind to contamination that might accumulate through environmental processes that the models had not considered. The regulatory framework that governed environmental protection at Soviet nuclear facilities embodied institutional confidence in mathematical analysis that reflected the broader, technological achievements of the Soviet nuclear program in reactor design, weapons development, and space exploration. Regulatory authorities had developed environmental protection requirements based on calculations that assumed worst-case scenarios for atmospheric and hydrological dispersion, but these calculations relied on the same simplified models that guided facility design and operation. The regulatory approach treated environmental protection as an engineering problem that could be solved through adequate mathematical analysis, proper implementation of calculated safety margins, and systematic monitoring of predicted contamination pathways. The contamination pathways that would eventually create the environmental disaster at Krasnoyarsk-26 were already present in 1967, embedded in the hydrological and geological characteristics of the site that the facility's environmental assessments had inadequately characterized. Seasonal patterns of precipitation and snowmelt in the Siberian climate created temporary flow conditions that violated the steady-state assumptions built into the facility's dispersion models. During spring snowmelt periods, river flow could increase by factors of 3 to 5 above average annual levels, creating flood conditions that inundated floodplain areas and altered normal patterns of water flow and sediment transport. Sediment deposits in the river bottom and extensive floodplain areas provided mechanisms for radioactive material accumulation that existed outside the analytical framework used to justify discharge operations. The dispersion models assumed that radioactive materials would remain dissolved in water and would be transported downstream according to surface water flow patterns, but they failed to account for chemical and physical processes that could bind radioactive materials to sediment particles, organic matter, and biological systems that operated according to entirely different transport mechanisms. Groundwater infiltration patterns in the permeable geological formations surrounding the facility created subsurface contamination pathways that could transport radioactive materials beyond the reach of surface water monitoring systems. The site's geological characteristics included extensive alluvial deposits and fractured bedrock formations that allowed significant interaction between surface water and groundwater systems, but the environmental assessments that justified facility siting had not fully characterized these subsurface flow patterns or their potential role in contaminant transport. The institutional culture within the Soviet nuclear establishment systematically reinforced confidence in simplified environmental modeling through organizational structures that separated reactor operations from environmental monitoring and assessment functions. Reactor operators focused on maintaining safe and efficient reactor operations according to well-established, procedures, and protocols, while environmental monitoring personnel focused on collecting data according to predetermined schedules and reporting results that remained within established action levels. This organizational separation prevented the development of integrated understanding of reactor operations and environmental impact that might have revealed the inadequacy of the model's underlying environmental protection strategies. The quality assurance procedures that governed environmental monitoring emphasized measurement accuracy and precision rather than comprehensive environmental assessment or validation of underlying modeling assumptions. Monitoring personnel received training that emphasized proper instrument calibration, systematic data collection, and accurate reporting of measurement results, but they received limited instruction in environmental science, hydrology, or ecosystem dynamics that might have enabled recognition of contamination transport through unpredicted pathways. The quality assurance approach assumed that accurate measurement of predicted parameters would provide adequate environmental protection, failing to recognize that the most significant environmental impacts might occur through processes that the monitoring program had not been designed to detect. The facility's waste management procedures reflected the same modeling limitations that governed reactor cooling and discharge operations. Liquid wastes generated through reactor operations, equipment maintenance, and facility decontamination were processed through treatment systems designed to remove radioactive materials to levels that would ensure compliance with discharge limits when diluted in the river system. The treatment systems operated according to removal efficiencies that had been determined through laboratory studies using simulated waste compositions under controlled conditions, but they had never been validated under the variable environmental conditions present at the actual discharge location. The chemical forms of radioactive materials present in facility waste streams reflected complex mixtures that resulted from reactor operations, fuel processing, and waste treatment processes. But the environmental models used to predict contamination transport assumed that these materials would behave according to simplified chemical and physical properties derived from laboratory studies of individual isotopes under idealized conditions. The models failed to account for chemical interactions between different radioactive materials, chemical interactions between radioactive materials and natural environmental constituents, and physical processes that could alter the environmental behavior of complex waste mixtures. The spring of 1967 brought hydrological conditions to the Yenisei River watershed that systematically violated every assumption embedded in the environmental safety calculations that governed operations at Krasnoyarsk-26. Unusually heavy snowfall during the preceding winter, combined with rapid warming temperatures in April and May, created snowmelt conditions that produced river flow rates significantly above the historical averages that had been used to validate the facility's dispersion models. These conditions initiated contamination transport through environmental pathways that the facility's monitoring systems had never been designed to detect. The hydrological event that triggered the environmental disaster began with meteorological conditions that fell within the range of natural variation for the Siberian climate, but exceeded the parameters that had been used to develop environmental safety calculations. Precipitation during the winter of 1966 to 1967 exceeded average levels by approximately 40% across the Yenisei watershed, creating snowpack depths that surpassed historical records in many areas. When spring temperatures rose rapidly during late April 1967, the accelerated snowmelt combined with concurrent precipitation to produce river flow rates that reached nearly twice the average spring flow levels that the facility's environmental models had assumed would represent maximum credible hydrological conditions. The facility's environmental monitoring systems first detected anomalous conditions during routine water sampling conducted at monitoring stations positioned downstream from the reactor discharge outfalls. On May 15, 1967, monitoring personnel recorded radioactivity levels in river water samples that exceeded predicted values by factors of 3 to 4, despite reactor operations that remained within normal parameters and discharge rates that remained well within established limits. The monitoring data indicated contamination levels that violated the mathematical relationships between discharge rates and downstream concentrations that formed the foundation of the facility's environmental safety calculations. Initial response to these anomalous monitoring results reflected institutional confidence in mathematical modeling that led facility management to assume that the unusual measurements resulted from instrument error or sampling contamination rather than fundamental inadequacies in environmental understanding. Quality assurance procedures implemented during the following week confirmed that monitoring instruments were operating properly and that sampling techniques remained consistent with established protocols. But additional measurements continued to show radioactivity levels that exceeded theoretical predictions by significant margins. The contamination patterns detected through expanded monitoring efforts revealed distribution characteristics that contradicted every assumption built into the facility's environmental models. Rather than following surface water flow patterns that would concentrate contamination immediately downstream from discharge points and gradually reduce activity levels with increasing distance, radioactivity measurements showed complex spatial distributions with concentration peaks in areas that dispersion models predicted should remain uncontaminated. Monitoring stations located several kilometers downstream from the facility detected radioactivity levels comparable to or higher than measurements recorded at stations positioned immediately adjacent to discharge outfalls. The reactor operations that produced this contamination remained entirely within design parameters and established safety limits throughout the period when environmental monitoring detected the anomalous contamination patterns. The 3 reactors at Krasnoyarsk-26 operated at power levels between 85 and 95% of rated capacity during May 1967, generating waste heat loads that required cooling water flow rates consistent with normal operational requirements. Discharge temperatures and radioactivity levels measured at the reactor outfalls remained within the ranges specified by operating procedures and environmental permits, indicating that the contamination detected in the broader river system resulted from environmental transport processes rather than abnormal reactor operations or procedural violations. The environmental processes that created these unexpected contamination patterns operated through mechanisms that the facility's safety assessments had never considered. The unusually high river flow rates created flood conditions that inundated extensive floodplain areas adjacent to the Yenisei River, establishing temporary water bodies where contaminated discharge water could accumulate and concentrate through evaporation and biological uptake processes. These floodplain pools received contaminated water during peak flow periods, but remained isolated from the main river channel as flow rate subsequently decreased, creating contamination reservoirs that persisted long after the hydrological conditions that created them had returned to normal levels. Sediment transport processes accelerated by high-velocity water flow carried radioactive materials that had been absorbed onto particle surfaces far beyond the locations where dispersion models predicted that contamination would be deposited. The increased river flow scoured sediments from the river bottom near discharge outfalls, resuspending previously deposited radioactive materials and transporting them downstream in concentrations that exceeded the levels that would result from contemporary discharge operations alone. This sediment transport created contamination sources at downstream locations that could persist and continue releasing radioactive materials into the water column long after the hydrological conditions that created them had ended. Groundwater infiltration processes that had been ignored in the facility's environmental assessments created subsurface contamination pathways that transported radioactive materials through geological formations surrounding the river system. The high river levels associated with flood conditions increased hydraulic pressure that drove contaminated water into permeable geological formations, creating groundwater contamination that could subsequently discharge into surface water systems at locations remote from the original discharge points. These groundwater pathways operated according to flow patterns and transport times that bore no relationship to the surface water dispersion models that had been used to justify discharge operations. The facility's environmental monitoring personnel initially attempted to explain the anomalous contamination patterns through modifications to existing dispersion models that preserve the fundamental assumptions underlying environmental safety calculations. Alternative explanations proposed during late May and early June 1967 suggested that unusual meteorological conditions had altered atmospheric dispersion patterns, that equipment maintenance activities had temporarily increased discharge rates above normal levels, or that sampling procedures had been contaminated by external radioactive sources. These explanations reflected institutional commitment to mathematical modeling approaches that prevented recognition that the fundamental assumptions underlying environmental protection had proven inadequate. Expanded monitoring efforts implemented during June 1967 confirmed that the contamination patterns detected in May represented persistent environmental conditions rather than temporary anomalies that could be explained through minor modifications to existing models. Additional monitoring stations established at locations throughout the river system detected radioactivity levels that remained elevated above background levels and above the concentrations that dispersion models predicted for those locations. The spatial distribution of contamination remained inconsistent with surface water transport models, and temporal variations in contamination levels showed patterns that could not be explained through variations in reactor operations or discharge practices. The environmental data collected during this period documented contamination transport through mechanisms that existed outside the analytical framework that had been used to justify discharge operations and establish monitoring protocols. Radioactive materials had accumulated in environmental systems through processes that operated according to timescales, transport pathways, and concentration mechanisms that the facility's safety assessments had never considered. The mathematical models that predicted contamination behavior under simplified laboratory conditions had proven inadequate for predicting environmental behavior under the complex, variable conditions present in real river systems. The recognition that environmental contamination was occurring through unpredicted pathways created operational uncertainty that challenged the fundamental assumptions underlying reactor operations and waste management practices. Facility management faced the unprecedented situation of operating nuclear reactors according to safety procedures that had been validated through mathematical analysis, while environmental monitoring data demonstrated that those mathematical models failed to predict actual environmental impact. The institutional frameworks that governed nuclear operations provided no guidance for decision-making under conditions where environmental safety calculations had proven systematically inadequate. The reactor cooling systems that created the contamination continued to operate according to design parameters that assumed environmental impact could be predicted and controlled through engineering calculations. The cooling water intake and discharge systems functioned exactly as designed, maintaining reactor temperatures within safe operating ranges while discharging waste heat and low-level radioactive contamination into the river system at rates that remained within established limits. The environmental impact of these discharges, however, occurred through pathways that the design calculations had never anticipated and that the monitoring systems had never been configured to detect. The procedural frameworks that governed reactor operations embodied assumptions about environmental predictability that prevented effective response to conditions where environmental models had proven inadequate. Operating procedures specified discharge limits and monitoring requirements based on calculations that assumed contamination would follow predicted transport pathways and would remain within calculated concentration ranges at specified downstream locations. When environmental contamination exceeded these calculated levels through unpredicted transport mechanisms, the procedures provided no guidance for operational adjustments that could address the actual environmental impact rather than the theoretical impact that had been calculated during facility design. The institutional culture within the facility management organization systematically reinforced confidence in mathematical modeling that prevented recognition of the fundamental inadequacy of environmental understanding. Management personnel had been trained according to approaches that emphasized systematic analysis, rigorous calculation, and adherence to established procedures as the foundations of nuclear safety. When environmental monitoring data contradicted mathematical predictions, the institutional response focused on identifying errors in measurement or analysis rather than questioning the validity of the underlying models that had guided facility design and operation. The hydrological processes that created unexpected contamination patterns at Krasnoyarsk-26 during 1967 operated through physical mechanisms that systematically violated the mathematical assumptions underlying environmental safety calculations. These processes did not represent equipment failure or operational error, but rather revealed fundamental gaps in scientific understanding of how radioactive materials interact with complex environmental systems under variable hydrological conditions. The contamination that developed during this period resulted from normal reactor operations that functioned exactly as designed, while environmental transport mechanisms operated according to physical laws that the facility's safety assessments had never incorporated into their analytical framework. The sediment transport processes that carried contamination beyond predicted pathways began with the mobilization of radioactive materials that had accumulated in river bottom deposits during previous years of routine discharge operations. The facility's environmental models assumed that radioactive materials discharged into the river would remain in solution and would be transported downstream according to surface water flow patterns. But actual contamination behavior involved complex interactions between dissolved radioactive materials and sediment particles that created long-term contamination sources in river bottom deposits. When high-velocity water flow during flood conditions scoured these contaminated sediments from the river bottom, radioactive materials that had been immobilized in sediment deposits were resuspended and transported downstream in concentrations that far exceeded the levels that would result from contemporary discharge operations alone. The chemical processes that governed radioactive material binding to sediment particles operated according to mechanisms that the facility's dispersion models had not considered. Cesium-137 and strontium-90, the primary long-lived isotopes present in reactor cooling water discharge, exhibited strong affinity for clay particles and organic matter present in river sediments. These chemical interactions caused radioactive materials to accumulate in sediment deposits at much higher concentrations than the dispersion models predicted, creating contamination reservoirs that could persist for decades and could be mobilized during future flood events. The mathematical models that predicted contamination transport assumed that radioactive materials would behave as conservative tracers that remained dissolved in water, failing to account for chemical processes that could concentrate contamination in environmental systems. The floodplain inundation that occurred during peak flow periods created temporary water bodies where contaminated water could accumulate and concentrate through evaporation, biological uptake, and sediment deposition processes. These floodplain areas, which the facility's environmental assessments had characterized as upland areas that would not be affected by routine discharge operations, became contamination concentration sites where radioactive materials could accumulate at levels that exceeded the concentrations present in the main river channel. As floodwaters subsequently receded, these contaminated floodplain pools remained isolated from the main river system, creating persistent contamination sources that could continue to release radioactive materials into local environmental systems long after the hydrological conditions that created them had returned to normal levels. The groundwater infiltration processes that created subsurface contamination pathways operated through geological formations that the facility's environmental assessments had inadequately characterized. The permeable alluvial deposits and fractured bedrock formations surrounding the Yenisei River allowed significant interaction between surface water and groundwater systems, but the environmental models used to predict contamination transport had treated surface water and groundwater as separate, non-interacting systems. During high river flow periods, hydraulic pressure drove contaminated surface water into groundwater systems, creating subsurface contamination that could subsequently discharge into surface water at locations remote from the original discharge points according to groundwater flow patterns that operated on entirely different timescales than surface water transport. The biological uptake processes that concentrated radioactive materials in aquatic ecosystems created contamination pathways that operated through mechanisms the facility's environmental models had never considered. Aquatic plants, algae, and microorganisms concentrated radioactive materials from water and sediments through biological processes that could increase contamination levels by factors of hundreds to thousands above the concentrations present in the surrounding water. These biological concentration processes created contamination in food webs that could persist and be transported through entirely different mechanisms than the physical transport processes that the facility's dispersion models had attempted to predict. The temporal evolution of contamination patterns revealed transport mechanisms that operated according to timescales that contradicted the assumptions built into environmental safety calculations. Rather than showing gradual decrease in contamination levels with time and distance from discharge points, monitoring data revealed complex temporal patterns with contamination levels that fluctuated according to environmental processes that operated independently of reactor operations and discharge practices. Contamination levels in some locations increased over time as environmental transport processes concentrated radioactive materials, while contamination levels in other locations decreased and subsequently increased again as environmental conditions changed. The spatial distribution of contamination violated every assumption about transport pathways that had been built into the facility's environmental protection strategy. Monitoring stations located several kilometers downstream from the facility consistently detected contamination levels that exceeded measurements recorded at stations positioned immediately adjacent to discharge outfalls, indicating transport mechanisms that concentrated contamination rather than diluting it with increasing distance from the source. The mathematical models that predicted contamination transport assumed monotonic decrease in contamination levels with distance from discharge points, failing to account for environmental processes that could concentrate contamination at remote locations. The radiological characteristics of environmental contamination revealed isotope ratios and chemical forms that differed significantly from the composition of reactor discharge, indicating environmental processes that selectively concentrated certain radioactive materials while dispersing others. Cesium-137 showed particularly strong environmental persistence and concentration in biological systems, while other isotopes that comprised significant fractions of reactor discharge showed more rapid environmental dispersion and decay. These differential environmental behaviors created contamination patterns with radiological signatures that could not be predicted from knowledge of reactor discharge composition alone. The hydrogeological processes that controlled groundwater contamination transport operated according to flow patterns and residence times that created long-term contamination sources in geological formations surrounding the river system. Contaminated groundwater moved through subsurface pathways at velocities that ranged from meters per year to meters per decade, creating contamination that could persist in groundwater systems for decades and could discharge into surface water systems according to seasonal variations in groundwater levels and hydraulic gradients. These groundwater contamination sources operated independently of contemporary reactor operations and could continue to contribute contamination to surface water systems long after reactor operations ceased. The geochemical processes that controlled radioactive material mobility in groundwater systems operated according to mechanisms that the facility's environmental assessments had never characterized. Chemical interactions between radioactive materials and geological formations could immobilize contamination in certain geological environments while enhancing contamination transport in others, creating complex spatial patterns of contamination that depended on detailed geological and geochemical characteristics that had not been adequately characterized during facility siting and design. These geochemical processes created contamination transport that could vary by orders of magnitude over spatial scales of meters to kilometers, making accurate prediction impossible without detailed understanding of subsurface geological and geochemical conditions. The thermal effects associated with reactor cooling water discharge created environmental conditions that altered chemical and biological processes governing contamination transport. The heated water discharged from reactor cooling systems created thermal stratification in river systems that altered mixing patterns and transport mechanisms in ways that the facility's dispersion models had not considered. These thermal effects could enhance biological activity that concentrated radioactive materials, alter chemical equilibrium that affected contamination solubility and transport, and create convection patterns that transported contamination through mechanisms that isothermal dispersion models could not predict. The environmental monitoring data collected during this period documented systematic failure of the mathematical models that had been used to justify discharge operations and establish environmental protection requirements. Every fundamental assumption underlying environmental safety calculations, uniform mixing, predictable dilution, conservative transport, and steady-state conditions, had proven inadequate for predicting contamination behavior under real environmental conditions. The facility operated according to discharge limits and monitoring requirements that had been derived from mathematical models that bore little resemblance to the actual environmental processes that governed contamination transport and accumulation. The emergency response procedures implemented at Krasnoyarsk-26 during late June and July 1967 reflected institutional commitment to mathematical modeling approaches that prevented recognition of the fundamental inadequacy of environmental understanding. Facility management attempted to address the environmental contamination through corrective measures that were designed, according to the same dispersion models that had failed to predict the contamination patterns, ensuring that stabilization efforts could not address the actual environmental processes that had created the problem. These response efforts demonstrated how institutional confidence in analytical approaches could perpetuate environmental damage even when monitoring data clearly indicated that existing models were systematically inadequate. The initial corrective measures implemented during the last week of June 1967 focused on reducing discharge rates to levels well below normal operational requirements in an attempt to minimize further environmental contamination. Reactor power levels were reduced to approximately 60% of rated capacity across all 3 reactors, decreasing cooling water requirements and allowing discharge rates to be reduced by approximately 40% below normal operational levels. These power reductions were maintained for 3 weeks, while environmental monitoring personnel attempted to correlate discharge rate changes with contamination levels measured at downstream monitoring stations. The environmental monitoring data collected during this power reduction period revealed that contamination levels in the river system remained elevated and showed no correlation with the reduced discharge rates that had been implemented. Monitoring stations throughout the river system continued to detect radioactivity levels that exceeded predicted values, and the spatial distribution of contamination remained inconsistent with surface water transport models even under the reduced discharge conditions. These results indicated that the contamination detected in the river system resulted from environmental transport processes that operated independently of contemporary reactor operations and discharge practices. The lack of correlation between discharge rate reductions and environmental contamination levels led facility management to implement expanded monitoring programs that attempted to identify the sources and pathways responsible for the unexpected contamination patterns. Additional monitoring stations were established at locations throughout the Yenisei River watershed, extending monitoring coverage to areas that had not been included in the original environmental surveillance program. These expanded monitoring efforts were designed according to systematic sampling protocols that emphasized comprehensive coverage of potential contamination pathways, but the monitoring station locations and sampling procedures remained based on dispersion models that had already proven inadequate for predicting contamination transport. The expanded monitoring program detected contamination at numerous locations where the facility's dispersion models predicted that radioactivity levels should remain at background levels. Monitoring stations established in tributary streams, groundwater wells, and floodplain areas detected contamination levels that indicated transport through environmental pathways that the original monitoring program had not been designed to assess. The detection of contamination in these remote locations confirmed that environmental transport processes had carried radioactive materials far beyond the areas where surface water dispersion models predicted that contamination should be present. The institutional response to these expanded monitoring results focused on identifying additional sources of contamination rather than questioning the validity of the dispersion models that had guided environmental protection strategies. Facility management initiated comprehensive surveys of reactor operations, maintenance activities, and waste management practices to identify potential sources of contamination that might explain the unexpected environmental monitoring results. These investigations examined equipment performance, procedural compliance, and operational records in detail, but they found no evidence of equipment malfunctions, procedural violations, or operational anomalies that could account for the environmental contamination patterns. The emergency response procedures that govern facility operations under abnormal environmental conditions embodied assumptions about contamination control that reflected the same modeling limitations that had created the environmental problem. These procedures specified corrective actions based on calculated relationships between operational parameters and environmental impact that assumed contamination transport through predicted pathways. When environmental contamination occurred through unpredicted transport mechanisms, the procedures provided no guidance for operational adjustments that could address actual environmental impact, rather than theoretical impact calculated through dispersion models. The revised discharge protocols implemented during August 1967 attempted to minimize environmental impact through operational modifications that remained based on the same mathematical models that had failed to predict the original contamination patterns. These protocols established discharge limits that were reduced to levels significantly below normal operational requirements and specified monitoring frequencies that were increased to provide more comprehensive surveillance of environmental conditions. The protocols assumed that reduced discharge rates combined with enhanced monitoring would provide adequate environmental protection, but they failed to address the environmental transport processes that had created contamination through mechanisms that monitoring systems could not detect. The waste treatment modifications implemented during this period attempted to reduce the radiological content of discharge through enhanced processing procedures that remained based on laboratory-derived removal efficiencies. Additional treatment steps were implemented to increase the removal of cesium-137 and strontium-90 from liquid waste streams before discharge to the river system. These treatment enhancements achieved removal efficiencies that exceeded design specifications under controlled laboratory conditions, but they could not address environmental contamination that had already occurred through transport processes that concentrated radioactive materials in environmental systems. The environmental remediation efforts attempted during late summer 1967 focused on contaminated areas that could be identified through surface monitoring, but these efforts remained systematically blind to subsurface contamination that had occurred through groundwater infiltration processes. Contaminated sediment deposits were removed from accessible areas of the river bottom near discharge outfalls, and contaminated soil was excavated from floodplain areas where surface monitoring detected elevated radioactivity levels. These remediation activities addressed contamination that was visible to monitoring systems, but they could not address contamination that had been transported through subsurface pathways that operated beyond the reach of surface monitoring techniques. The long-term monitoring programs established during this period attempted to provide comprehensive surveillance of environmental conditions through systematic measurement of radioactivity levels at locations throughout the river watershed. These monitoring programs were designed to detect changes in contamination levels that might indicate the effectiveness of corrective measures or the development of new contamination sources. The monitoring procedures emphasized measurement accuracy and systematic data collection, but they remained based on sampling strategies that reflected the same modeling assumptions that had proven inadequate for predicting contamination transport through complex environmental systems. The institutional analysis of the environmental situation conducted during autumn 1967 focused on identifying procedural improvements and equipment modifications that could prevent similar environmental problems in the future. This analysis examined the adequacy of environmental monitoring systems, the effectiveness of waste treatment processes, and the reliability of discharge control mechanisms. The analysis recommendations emphasized enhanced monitoring coverage, improved waste treatment efficiency, and more restrictive discharge limits, but they did not address the fundamental inadequacy of environmental modeling that had created systematic blind spots in environmental protection strategies. The scientific studies initiated during this period attempted to improve understanding of contamination transport through environmental research programs that remained constrained by the analytical approaches and computational limitations that had created the original modeling deficiencies. These studies examined contamination transport through controlled experiments and mathematical modeling efforts that attempted to refine existing dispersion equations rather than developing entirely new approaches to environmental analysis. The research programs provided useful data on specific aspects of contamination transport, but they could not address the fundamental complexity of environmental systems that made accurate prediction impossible through simplified mathematical models. The regulatory review of facility operations conducted during late 1967 examined compliance with environmental protection requirements and evaluated the adequacy of existing safety calculations. This review confirmed that facility operations had remained within established limits and that monitoring procedures had been implemented according to approved protocols, but it did not address the fundamental inadequacy of the mathematical models underlying environmental protection requirements. The regulatory analysis focused on procedural compliance rather than environmental effectiveness, reflecting institutional commitment to analytical approaches that had proven systematically inadequate. The operational modifications implemented as permanent corrective measures reflected continued confidence in mathematical modeling approaches combined with recognition that existing calculations had underestimated environmental impact. Discharge limits were permanently reduced to levels approximately 50% below original design specifications, and monitoring requirements were permanently enhanced to provide more comprehensive environmental surveillance. These modifications addressed environmental impact that could be predicted through existing models, but they could not prevent future environmental problems that might occur through transport processes that remain beyond the analytical framework used for environmental protection. The facility continued to operate according to environmental protection strategies that embodied the same fundamental assumptions about environmental predictability that had created the original contamination problem. Despite clear evidence that environmental transport processes operated through mechanisms that existing models could not predict, institutional commitment to mathematical analysis prevented recognition that environmental protection required entirely new approaches to understanding complex environmental systems. The corrective measures implemented during 1967 addressed symptoms of environmental modeling inadequacy, rather than the fundamental limitations of analytical approaches that made accurate environmental prediction impossible under real-world conditions. The long-term environmental investigations conducted at Krasnoyarsk-26 during the decade following the 1967 contamination event revealed the true extent and persistence of environmental damage that had occurred through processes that the facility's safety assessments had never considered. These investigations provided definitive evidence that the facility's environmental models had been systematically inadequate from inception, and that the contamination detected in 1967 represented only a fraction of the total environmental impact that had accumulated through years of routine operations that remained technically compliant with established safety requirements. The comprehensive environmental surveys initiated in 1968 employed monitoring techniques and analytical methods that had not been available during the original facility siting and environmental assessment processes. Advanced radiological detection equipment with enhanced sensitivity and improved isotope discrimination capabilities revealed contamination patterns throughout the Yenisei River watershed that extended far beyond the areas where previous monitoring had detected elevated radioactivity levels. These surveys documented contamination in groundwater systems, soil profiles, sediment deposits, and biological systems at locations up to 50 kilometers downstream from the facility, indicating environmental transport through mechanisms that the original dispersion models had never anticipated. The isotope analysis conducted during these expanded investigations revealed contamination signatures that confirmed transport through multiple environmental pathways operating on different timescales and according to different physical and chemical processes. Cesium-137 concentrations in river sediments showed accumulation patterns that indicated decades of gradual deposition and concentration through biological and chemical processes that operated independently of surface water flow patterns. Strontium-90 distributions in groundwater systems revealed contamination transport through subsurface pathways that operated according to geological flow patterns with residence times measured in decades rather than the days to weeks assumed by surface water dispersion models. The retrospective analysis of meteorological and hydrological data conducted during this period revealed that the 1967 contamination event represented the culmination of environmental processes that had been occurring throughout the facility's operational history. The unusual precipitation and snowmelt conditions that occurred during spring 1967 had created hydrological conditions that mobilized contamination that had been accumulating in environmental systems since reactor operations began in 1958. The mathematical models that had been used to predict environmental impact had failed to account for long-term accumulation processes that could create contamination reservoirs in environmental systems that would persist for decades and could be mobilized during future hydrological events. The biological monitoring programs established during the late 1960s documented contamination concentrations in aquatic ecosystems that exceeded the levels present in water and sediments by factors of hundreds to thousands, confirming that biological uptake in concentration processes had created contamination pathways that operated according to entirely different mechanisms than the physical transport processes that environmental safety calculations had attempted to predict. Fish, aquatic plants, and benthic organisms throughout the river system showed contamination levels that indicated systematic uptake and concentration of radioactive materials through food web processes that had never been considered in environmental impact assessments. The geological investigations conducted during this period revealed subsurface contamination patterns that confirmed transport through groundwater systems with complex three-dimensional flow patterns that bore no relationship to the surface water transport models that had been used to justify discharge operations. Contaminated groundwater had infiltrated permeable geological formations throughout the river valley, creating subsurface contamination sources that could continue to discharge radioactive materials into surface water systems for decades, according to groundwater flow patterns that operated independently of surface water conditions and reactor operations. The ecological studies initiated during the 1970s documented contamination persistence in environmental systems that contradicted every assumption about environmental recovery that had been built into the facility's safety assessments. Rather than showing gradual decrease in contamination levels through radioactive decay and environmental dispersion, many environmental systems showed persistent or increasing contamination levels as biological and chemical concentration processes continued to accumulate radioactive materials from diffuse environmental sources. These studies revealed that environmental contamination created through complex transport and accumulation processes could persist in environmental systems for time periods that exceeded the operational life of the reactors that had created the contamination. The epidemiological studies conducted in downstream communities during the 1970s and 1980s provided evidence of health impacts that confirmed that environmental contamination had reached human populations through exposure pathways that the facility's safety assessments had not considered. Increased cancer rates in communities located along the Yenisei River downstream from the facility indicated contamination transport through environmental systems that had carried radioactive materials to populated areas despite dispersion models that predicted contamination levels would remain below levels of health concern at these locations. The regulatory analysis of the Krasnoyarsk-26 environmental situation conducted during the mid-1970s concluded that the facility's environmental protection requirements had been based on mathematical models that were fundamentally inadequate for predicting environmental impact under real-world conditions. This analysis recommended comprehensive revision of environmental protection requirements for nuclear facilities to incorporate understanding of complex environmental transport processes that had been revealed through the Krasnoyarsk-26 experience. The regulatory recommendations emphasized the need for environmental monitoring programs that could detect contamination transport through multiple environmental pathways, rather than monitoring programs based on theoretical predictions of contamination transport. The scientific research programs initiated in response to the Krasnoyarsk-26 environmental situation led to fundamental advances in environmental science and radioecology that transformed understanding of how radioactive materials interact with complex environmental systems. These research programs developed new mathematical models that incorporated biological uptake processes, chemical concentration mechanisms, and multi-pathway transport that could provide more realistic predictions of environmental impact under variable environmental conditions. The research results demonstrated that accurate prediction of environmental impact from nuclear facilities required comprehensive understanding of environmental systems that extended far beyond the simplified dispersion models that had been used during the early decades of nuclear power development. The facility decommissioning studies conducted during the 1980s revealed the full extent of environmental contamination that had accumulated during 3 decades of reactor operations that had remained technically compliant with environmental protection requirements throughout the facility's operational life. Environmental contamination surveys conducted in preparation for facility closure documented contamination in soil, groundwater, and biological systems throughout a watershed area exceeding 1,000 square kilometers, indicating environmental impact that exceeded the original environmental assessments by orders of magnitude. Contamination patterns revealed through these comprehensive surveys confirmed that environmental transport had occurred through mechanisms that the facility's safety assessments had never considered, and that could not have been detected through monitoring programs based on simplified dispersion models. The environmental remediation efforts implemented during facility decommissioning revealed the practical impossibility of addressing environmental contamination that had been dispersed through complex environmental systems according to transport mechanisms that operated over multiple spatial and temporal scales. Contaminated soil and sediment could be excavated and disposed of through conventional remediation techniques, but contamination that had been transported through groundwater systems and biological pathways had become integrated into environmental systems in ways that made complete remediation technically and economically infeasible. The long-term environmental monitoring programs established to assess environmental recovery following reactor shutdown documented contamination persistence in environmental systems decades after cessation of contamination sources, confirming that environmental impact from nuclear facilities could persist for time periods that exceeded human institutional timescales. These monitoring programs revealed that environmental systems that had been contaminated through complex transport and accumulation processes would require decades to centuries for natural recovery processes to reduce contamination levels to background conditions. The institutional analysis of the Krasnoyarsk-26 environmental situation conducted during the 1990s identified fundamental flaws in the approach to environmental protection that had characterized nuclear facility development during the early decades of nuclear power. This analysis concluded that environmental protection based on simplified mathematical models and theoretical safety calculations was systematically inadequate for protecting environmental systems and human health under real-world conditions. The analysis recommended that environmental protection for nuclear facilities be based on comprehensive understanding of environmental systems, conservative assumptions about environmental transport processes, and monitoring programs capable of detecting contamination transport through multiple environmental pathways. The Krasnoyarsk-26 environmental contamination ultimately demonstrated that nuclear facilities required entirely new approaches to environmental protection that recognized the fundamental complexity and unpredictability of environmental systems. The mathematical confidence that had characterized nuclear facility development during the 1950s and 1960s had proven systematically inadequate for predicting environmental impact under real-world conditions, and environmental protection required acknowledgement of scientific uncertainty, rather than confidence in theoretical calculations that could not account for the full complexity of environmental transport and accumulation processes.